Hi, and welcome back to the HeFPipe tutorial. This video is going to talk about the generation of RMES, GEPHAST, and RHH related files. So the first of these files to be generated is the one formatted for RMES, which stands for Robust Multi-Locus Estimate of Selfing. Note that RMES only operates on Windows platforms, so the RMES ready file may need to be opened in Microsoft Word and then transferred between operating systems in that format to preserve format integrity. So you can see the RMES formatted file here, rmesready.txt. And again, you may just want to select all, copy, and paste into Microsoft Word so that you can go across platforms a little more easily. That's the way at least I've had success with RMES rather than just transferring this text file, which can sometimes have issues across operating systems. The pipeline also generates at this point a directory called GEPHAST ready, and that contains CSV formatted files, here it is, for each trait column in the trait file. Remember, the trait file in our case is called acceptor.csv, it's right here. So for each trait column in this CSV file, like that, in the pipeline in GEPHAST ready, a file is created for each of those. And it's formatted in a way that the GEPHAST macro in Microsoft Excel can be run on it. So you get to run GEPHAST on as many or as few of these CSV files as desired. So, pick the traits that you want to look for single locus associations in. And after each test has been completed, save the CSV files containing those results into a separate directory that you create yourself. So in our case, we created a directory called GEPHAST tested, and in the example data, I already ran GEPHAST on 3 of the traits, V1, V2, and V3. But I'm going to go ahead and run GEPHAST once so that you see how it's done. So the first thing you do is in the installation package, you have the documentation and the Excel macro for GEPHAST. So when you open that, it might ask you whether you want to enable macros, and clearly you do, because GEPHAST is a macro. So you open GEPHAST, and then you open one of the traits you are curious about. So in our case, let's look at V1. So here is what a GEPHAST formatted file looks like. The first column is just population. Since we're doing a heterozygosity-fitness correlation, there's only one population. So that'll just be 1. And then you have trait values for that trait. So in our case, this is a binary trait. And then you have all of the locus genotypes. So we select all, we go to Tools, Macro, look at the macros, and the one you want is main. Click Run. It'll ask you which type of analysis we are doing using a binary trait. So I'll run option 1. Let's do 100,000 randomizations. And this will run for a few minutes. Okay, so we're back and GEPHAST ran, and you can see that at the end of the run, you'll have p-values displayed at the bottom of each alternating column. So each, per locus, these 2 columns are alleles in this one locus. Actually, they're p-values multiplied by 100, but they're p-values. So again, I'll save this file into a separate directory, which in our case, remember, is called GEPHAST tested. So in the pipeline, we'll go to GEPHAST tested, and we'll just save it as V1, comma separated value file. And since there's already 1, we'll just replace it. After you've done this for all of the traits that you care about, The pipeline is going to ask you whether you want to create a list of GEPHAST p-values for the traits for which you've run the GEPHAST macro on. And let's say we do want to do this. It's then going to ask us to check one more time, so don't proceed until you've run the GEPHAST macro on the relevant spreadsheets and saved the output spreadsheets into a directory of your own making where they can be processed. So yeah, we've done that. We'll press any key to continue. Then it'll ask you what the address of that directory is. So again, all the CSV files in that directory will be treated as if they are the results of a GEPHAST simulation. So in our case, we know that this directory is GEPHAST tested. So we'll take that directory and drag it onto terminal. Again, being aware that this space is created at the end and being aware that since it's a directory, we should end in a backslash. Now we press enter. So the pipeline generates two files from that, GEPHAST pvalues.csv right here, and GEPHAST padjusted.csv. These contain the p-values, or p-values adjusted from multiple comparisons using the Benjamini-Hochberg procedure and assuming an 5% false discovery rate, respectively, for tests of significant single locus associations for each trait at each locus for which there were a result file in the designated GEPHAST results directory. So let's open p-vals. And as you can see, the p-values are listed every other column, while the loci are listed in the other columns here, here, and here. The trait names are the headers for the odd columns. And the multiple comparisons in the pipeline were applied at the trait level, not the global level. Note also that these files aren't sorted by p-value. Okay, so next the pipeline creates a file that it can pass to the R package RHH. And this file is called rhhready.txt. You can see it right here. So the pipeline just generated this automatically. It also generates three other files at this point. A file called heterozygotes and homozygotes.csv, which is right here. And in this file, all the diploid genotypes from final output.csv, which we looked at in an earlier video, they've been converted into 1 if they are heterozygous and 0 if they are homozygous, and NA if there are data missing. And notice the information for each locus has been compressed into one column in this file instead of two. So now it's just homozygote, heterozygote instead of two different alleles. The second file it creates is called Mlh Calculated Csv, which is here. And this file just contains the multi-locus heterozygosity values for each sample that was in the final output.csv file, which we looked at in an earlier video. So we just calculated multi-locus heterozygosity, which is just the proportion of heterozygous loci over loci typed for each individual. The third file is a file called loci typed per individual, and it's right here. And it contains the number of loci at which each individual was successfully genotyped. So here are all of the different individuals, and here's the number of loci that were successfully genotyped at. At this point in the pipeline, you're prompted to run the RHH script, which conducts the heterozygosity correlation test, or HHC, for identity disequilibrium and inbreeding. As it's currently configured, the script runs through 250 iterations, but it's possible to change this value in the actual Python program. So if you're ready to run this script, type yes, and it'll run for a few minutes. Okay, the RHH script finished running, So at this point, the script generates several documents. The first is number of alleles.txt, and you can see that here. And it literally just displays the number of alleles for each locus. The second file is RHH test output.txt. Here we are. And the third is RHH test output.txt CSV converted.csv right here. And these are just a CSV and a text version of each other that have each sample, its internal relatedness value, standardized multi-locus heterozygosity value, and its homozygosity by locus value, which, recall, are just different ways of estimating multi-locus heterozygosity. So you had MLH in a different document, and now you have IR, SH, and HL here. And the fourth is called the hhcplot.pdf, and that's right here. And it's a plot of the distribution of correlation coefficients generated by the heterozygosity correlation test. Fifth, a file gets created that's called mean and core probs.txt right here. And it displays the mean correlation coefficient and 95% confidence intervals for the HHC test. So here is the mean, and here are the confidence intervals. The pipeline also generates a file called Mlh Output Csv, which combines Mlh, IR, SH, and HL values, which were calculated previously, with the values from the trait file, which, recall, is called acceptor.csv. So this file is sort of the master trait and heterozygosity file. So here are all the traits, and then here are the heterozygosity values for each sample. Now it is this file that gets used downstream by the pipeline for all the regression analyses. So after exiting the RHH module, the pipeline creates a file called number of samples per locus, which is right here. And this file is a spreadsheet that contains two columns. The first column is a list of all the loci in the locus to include list or keep list file. And the second column lists the number of samples at which each of these loci were successfully scored. And that's it for this installment. Stay tuned for a continuation of the pipeline.